Okay, so today I thought we would work on a problem from Morin again. We've been looking at things like the area under the projectile's trajectory. What about the arc length? In other words, is there a way to choose our angle theta, or launch angle theta, so that we maximize the entire length of this parabolic arc before it hits the ground? So recall, we have previously calculated the velocity components at any time t as it's flying through the air. We also calculated the total time that it would take to hit the ground. And now what we want to do is calculate this arc length. So recall that the arc length has to be calculated using calculus here. So we'll have an integral of little tiny chunks of the arc that have been added together over this entire interval. Each little chunk of arc can be thought of as the hypotenuse of a very, very small triangle. Dx by dy. However, can't really do the integral as written. So what we'll do is we'll use the parametric form of this projectile to rewrite our dx's and dy's in terms of dx dt's, dy dt's, and then pull out our integration factor or our integration measure of dt. Okay, so that gives us our integral that we have to perform. And now we can see that dx dt is simply vx, and dy dt is simply vy, and we again have our parametric versions of those. That's kind of nice. We also now know what we can use for the bounds of this integral since we are integrating over the entire time. Notice that we could take 0 to t, capital T, the total flight time that we have here, or we can just double the time it takes to go halfway. I'm going to do that just for symmetry, so we'll start at time 0, and then we'll go up to t over 2, which is halfway there, but we know by symmetry that the arc length will be symmetric around the vertex, so we'll just double that altogether. Notice that as it is, most of these things are constants, so it might be kind of nice for us to do some sort of u substitution to rewrite this in terms of something that we can integrate over and pull out as much as we can from this integrand. Using our result for t here, and then don't forget we're dividing by 2, I'll have a v naught sine theta over g as my upper limit. I'm going to go ahead and factor out the v naught squared cosine squared term from both of these terms, which will go ahead and just give me a v naught cosine theta in front of this whole square root. We'll be left with a 1 here, and then I'll have v naught sine theta over v naught cosine theta, which is going to be tan theta. And then the gt, unfortunately, does still have a v naught cosine theta left in its denominator. That's still all squared. So we end up with this integral left. And now we can see that this bit in parentheses is begging to have a u substitution performed. So let's do that off to the side here. Let's set u equal to tan theta minus gt over v naught cosine theta. That means that du will be negative g over v naught cosine theta dt. We can also see that when t is 0, we have u is simply tan theta. And we can also see that when t is equal to v naught sine theta over g, plugging that in for our t right here, the v naught and the g will cancel out. I'll end up with sine theta over cosine theta, which is tan theta, but I'll have tan theta minus tan theta. which means u is equal to 0 at that point. Another reason why it's kind of convenient to make this substitution. So after doing that and pulling this v naught cosine theta out to the front, also while I'm doing that, I'll go ahead and replace my dt by negative v naught cos theta over g du, which picks up a square on both of these terms. I do pick up a g here, and I do pick up a negative sign, but we'll see what happens to that in a second. What's left will be the integral from, well, t equals 0 gave me a tan theta for u, and t equals this thing gave me a 0 for u. I have my square root, 1 plus, again, this whole thing is just u, quantity squared. And then my dt I've already converted into a du, and I factored all of those constants out to the front and combined them. So this is our result. Notice we can make one quick additional substitution or simplification. I'll use the negative sign here to replace my bounds of integration with a flip. So this is the integral we now have to perform. Okay, let's bring this up to the top and see if we can't do that integral together. Okay, I'm going to pick another substitution to do here. And there are a couple different choices you can choose. You could try to do a trigonometric substitution, which is fine, that will work. Since I already have some trig functions of theta, maybe I want to try something a little different. So what I'm going to actually use is a hyperbolic trig substitution, partly because I think that the hyperbolic functions are just a little unloved. They really need a little bit more exposure in the real world. So let's go ahead and choose a new substitution, which is u equals hyperbolic sine of x, or I'll read that as sinh. In that case, du is going to be cosh hyperbolic cosine of x dx. Sinh and cosh have this nice derivative property similar to the circular trig functions. Notice that when u is equal to 0, we have x equals 0, so that's the same, no issue there. We do have this kind of annoying bit, which is when u equals tan theta, I'm going to invent a new symbol, I'll call it x1, which will simply be the inverse hyperbolic sine of tangent theta. Okay, so that'll just be a placeholder variable for the upper limit of integration. When we make those substitutions, and keeping in mind those for later, we end up with this result. Let's also include a few of the hyperbolic trigonometric identities that we'll need to simplify this. We have our Pythagorean identity, just like we do in the circular trig function case, except we have a minus sign instead of a plus sign. Let's also include the power reduction identity for cosine, or cosh. So notice this is a square, this is a double, so we'll probably want to use that for doing our integral. And let's also write down the double angle identity for hyperbolic sine. So notice this looks a lot like the double angle identity for the circular trig function sine. Okay, so 1 plus sinh squared is going to be cosh squared, but it's under a square root and everything here is positive, so that'll just be cosh. But we do also have this cosh that came from doing our Jacobian, or change of variables, so we should also include that. Okay, so we've reduced this down to doing a cosh squared antiderivative. This is where our power reduction formula will come in, so let's apply it. Notice that this 1/2 out front can cancel with the 2 here. The antiderivative of cosh is sinh. And because we have this 2 here, don't forget that we do end up getting a 1/2. The antiderivative of 1, of course, is just x. Pretty obviously, when we plug in x equals 0 to both of these, we'll get 0. So we're ending up with an x1 in both of these locations. While we're at it, though, let's go ahead and apply our double angle identity for sinh. This 2 out front and this 1/2 out front will also cancel for this term, and I'll be left with sinh x cos x. So let's write that. Okay, we're almost done. Let's bring our result that we have here up to the top, and we'll play around with what to do with these x1s, which recall were defined in terms of tan theta. Okay, so here's what we had from before. Notice that when I take the hyperbolic sine of the inverse hyperbolic sine, those will cancel out and I'll just be left with a tan theta. We do have to figure out how the hyperbolic cosine and the arc hyperbolic sine interact with each other. Of course, you could go look it up, but we could also think about this in terms of a little triangle. Curiously, it's a triangle on a unit hyperbola, or conversely, a triangle in a Lorentzian signature two-dimensional space. But let's imagine a small triangle here. I'm thinking of this arc sine or arc sinh as being tan theta over 1. So if I call this x1, and I think about this as, well, sinh should be something like opposite over hypotenuse in some hyperbolic space, this would be like tan theta and 1. Now, normally you would apply the Pythagorean theorem to find what this last side is, but we don't actually have the Pythagorean theorem here. We have cosine squared minus sine squared, or this side squared, this minus this sine squared equals my constant hypotenuse. So this is actually going to end up being square root of 1 plus tan squared, not 1 minus tan squared like you might think if you're thinking hyperbolically. But 1 plus tan squared is secant squared, and square root of secant squared is secant. So if I want to rewrite hyperbolic cosine of the arc hyperbolic sine of an argument, I'm going to end up with adjacent over 1, which will simply be secant. Putting it all together, we said this part was already tangent. This part is now secant theta. This part we have to leave as the inverse hyperbolic sine of tan theta. Distributing things through, this cosine squared will actually take care of the cosine in the denominator of tangent. It'll take care of the cosine in the denominator of secant, and I'll just be left with a sine. I think this is a nice final form. It's relatively compact. We can see the dimensionality out front nicely. The only price we pay is this inverse hyperbolic sine. Now, if you're interested, you can always replace inverse hyperbolic functions with logarithms. In fact, I'll write it off to the side. So there are many other ways of rewriting this. The tan theta that would show up in this logarithm would be squared here. You'd get another secant, and you have tangent plus secant. So the natural log of tangent plus secant, you could also there combine denominators and get something like, I guess, sine theta plus 1 over cosine theta inside the logarithm. I prefer to leave it this way. Okay, so this is our expression for the length as a function of the launch angle theta. Now our question is, let's maximize this. So I'm going to bring this up to the top, and we'll try taking the derivative. Okay, there's our result. Let's go ahead, take the derivative of this with respect to theta, set it equal to 0, and see if we can maximize it. Notice that, of course, the constants come out to the front. We're just doing a theta derivative. The first term is quite easy. That'll give us a cosine. The second term is a little more complicated because it is both a product rule and we have our chain rule. So we'll do it piece by piece. There's the first term in our product rule. The cosine squared ends up being 2 cosine derivative of cosine, leaving the arc sine or arc sinh off to the side. The second term will be cosine squared times the derivative of the inverse hyperbolic sine. And then, of course, we apply the chain rule. The derivative of tangent is secant squared. Okay, it looks a little messy, but actually it's not quite so bad. A lot of stuff simplifies down. For example, 1 plus tan squared is, again, secant squared. Square root of secant squared is secant. And of course, it's in the denominator, so this secant and one of these secants cancel out. We also have cosine squared times secant gets rid of one of those cosines. So this second term is just cosine theta. Notice there's also a cosine theta in the front here, so I get 2 cosine theta for those two. We also have a 2 cosine theta here times some stuff. So let's go ahead and pull out 2 cosine theta from this whole expression. We'll be left with a 1, remember this was 1 plus 1, minus sine arcsinch tan theta. And I want this to equal 0 to maximize that derivative. Well, cosine theta equals 0 gives me kind of a trivial result. I mean, I suppose in a way you could ask, what's the minimum arc length at a given v naught? And that would just be firing it straight up. Okay, so cosine theta equals 0 means theta equals 90. That does give me a minimum L, but I want a maximum L. That's when this term in parentheses is equal to 0, which means it is the angle that satisfies this transcendental equation. Now, unfortunately, solving this analytically is impossible, but you can go ahead and calculate the numerical value, which ends up being about 56.466 degrees. That's kind of interesting. It's a little bit larger of a launch angle than the 45-degree maximum range angle. If you're also interested, you can take this theta star, this maximal length angle, plug it back into your expression for L and see what happens, what is actually the maximum length. So notice that since theta star satisfies this relation, I can replace this arcsinch of tan theta with 1 over sine in this formula. But if we find a common denominator here of sines of this theta star, I'll end up with a sine squared plus cosine squared over sine, which is just the cosecant. And now if you take this numerical value of theta that was calculated earlier and plug it in here, we can end up with an approximate value for our maximal length. Notice that since v naught squared over g was the maximal range, the maximal length of your parabolic arc is about 20% larger than your maximum range, and that occurs when you fire it at this particular angle. QED.